Hi guys, Mark here, and today we're looking at the solution to day 22 of the Advent of Code challenge. And today's challenge really carries on from yesterday. We're still in our game where we're fighting against the boss, but instead of just fighting him with weapons, we are fighting with magic spells. And we've got a variety of magic spells that we can buy from the shop. Each one costs a different amount of these mana points, and each one has got different things it does. Some of them damage the boss, some of them increase your armor or give you more mana points or something like that. And so basically the challenge is, what is the minimum amount of mana we can spend and still beat the boss? And so basically we've got to work out how to fight these battles using these spells, and thankfully we get some quite detailed examples of two battles that help us work out how to implement the rules. So let's start off by going over to my C# code, because I initially attempted this in C#, and I decided I would make a base class for spell and then implement each of the various spell types in derived classes. And actually this was probably overkill. We could have made a base spell class that was powerful enough to do all of the spells. But some of the spells are what's called effects. They last for several turns, whereas others of them are one shot and they just operate immediately. So we have the magic missile, which adds 4 hit points. We have the drain, which increases your health. And then we have some effects like the shield, which for 6 turns increases your armor. And you'll probably notice here that I've got some debug statements in. And what I wanted to do that for was so that I could play out some battles and check that my output matched the output shown here in the test cases. And so if we go down to my battle function, you can see that we start with the player and the boss, and we have the spell chooser interface, which I'll show you in a moment, that basically allows us to choose what the next spell we should use is, and allows me to play out some of the example cases by returning different spells in a specific order. And the hard flag was for part B of the problem. There's a special hard mode where you lose a point at the start of every turn. And so what I do is, while both players are alive, I print out my debug saying what their status is. I then use the spells on the player, and I call my spell chooser to get the next spell, and then we add that spell that we've chosen to the player, and then before the boss has his turn, the player gets to use their spells again, and then the boss hits the player, and we keep going like that. Now if we actually look at the player status class, one of the interesting things you might notice is that despite what I talked about yesterday in the benefits of having immutable classes, today I decided not to use an immutable class, because in C# working with immutable types can be a little bit of a pain because the language really isn't set up to make that easy for you. And I also decided that I was going to fight every battle individually from beginning to end. I wasn't going to go and try and branch off and leave battles half fought while exploring possibilities of what way they would go if a different spell was chosen. And the reason I wanted to do that was I wasn't even sure how many possible battles there were. There was a real risk, I think, in this problem of the total number of battles, potential battles that could be fought, being so high that we couldn't brute force it. And so I wanted to make sure that I could run a battle from beginning to end and see how much mana was spent winning the battle, and then try a different battle and abandon that battle if the amount of mana spent was higher than the best that we'd got. And so that was one of the reasons behind having this interface, if I can find it, the spell chooser interface. So when we call get next spell, when I'm running my test cases, I've just got a very simple queue spell chooser that just returns the next spell from a list. So if we go to the bottom here, you can see that I can run a test battle by setting up 2 test players, setting up the spells in order that the test player will choose, and then putting that into a queue spell chooser. So if I run this, I can see the output from this battle, and I can see that I can check that all of my implementations of the various spells are working as expected. And yes, it probably took me longer to code because I put this in, but it also helped me to track down some problems more easily. What about actually solving the problem though? What is the minimum amount of mana we can spend to beat the boss? Well, I need to create my player object and my boss object, and I'm going to battle them 10,000 times. That's just an arbitrary number I chose, so that if my algorithm was running too long, I could try and optimize it a bit more, and passing in my spell chooser object. So let's have a look at how the spell chooser works. And this, in a way, is a little bit ugly, because what I do is, to get the next spell, I look through all of the possible spells, see if we can afford it. Its cost is later less than the amount of mana we've got. See if the amount we'd spend is less than the best winning amount that we've seen so far. Otherwise, we're going to abandon this battle. And we also can't reuse the same spell that is already active. So we'll return either nothing, if there are no valid spells, or a random spell. And this might surprise you a little bit that I've gone for random here. There certainly would be more systematic ways of doing this, but I just wanted to just try something very simple to get me started. And because the spells are mutable, I actually have to, rather hackily here with activator create instance, make a new instance of the spell so that its timer is set back to its maximum value. So that's a bit ugly and probably should be refactored. So if we go down to the bottom here, we will see that, let me take it off hard mode and put it back onto easy mode for part A. And we'll run this. We'll see that it initially found the best amount of 1,422. And you can see here that it shows me what was used in reaching that amount, which is also helpful for debugging. But you can see that we slowly get lower and lower best amounts. And this one returned a best amount of 1269, which was the correct answer, as you can see from my comments. You can also see from my comments that I had a lot of incorrect answers here. I first of all gave an answer of 854 because I thought you could have two of the same effect active at once. Then I tried 900 after fixing that bug, and the website accused me of cheating. Apparently 900 was the answer for someone else's problem. Then I realised I hadn't even managed to copy my boss's status in properly. My boss had 58 health and I'd only been putting 50 in there. And so when I got that right, I got an answer of 1235, and I was sure that this time I would have the right answer. And by this time the website was telling me you have to wait 5 minutes between entering answers, but that was wrong. And so it was back to the debugging, and eventually I discovered I wasn't actually letting the shield wear off. And so finally 1269 was the right answer. And I found actually, although I've got 10,000, even 1,000 iterations was getting me to the lowest one. Pretty much every time I ran this, it was finding that. Now for part B was thankfully a lot easier. If you looked on the leaderboard today, it didn't fill up until a good 3 hours had passed. I'm not sure exactly how long it took me to solve today's challenge, but it certainly was in several hours of time. So for part B, if I set this to true, I found it did need to have more time, more iterations around this loop to converge on the lowest answer, 1382. No, this time it didn't. So I had to run it a few times. And 1309 turns out, probably I should have set that to about 100,000 iterations. 1309 turns out to be the lowest amount that can beat the bad guy. Okay, so I don't know what you think of this solution. It's certainly not particularly pretty, either in coding or in the algorithm I used to solve it. And given how much time I spent on getting this working, and because of the silly bugs I made along the way, I didn't really have loads of time to say, let's re-implement this in F sharp. But when I went onto the subreddit, I found that somebody had already put a really nice looking F sharp solution. So let's just have a look at this, and I'll give full credit to Lincoln A, who posted this. Here's the link to where he posted it, and this is, I think, a really elegant solution, although it does have one problem. And basically he's used a record type for the spell, and this is really a much more sane way of setting up the spells. Make them generic. Each spell has a cost, amount of damage it inflicts, amount it heals you, amount of armor it gives you, amount of mana it gives you, and a number of turns that it lasts for. And then he's created a recursive play function that says whether it's my turn or the boss's turn, how much I've spent so far, what part of the problem we're on so that we can solve part B, and various amounts, my status, my health point, mana, and the spells I've got active, and my boss's status, his health points, and how much damage the boss can cause. And it returns a sequence of int options. So in other words, it's returning either some int or none. And it returns none if we lose, and it returns some int if we win with how much we spent. And so if we've died in part 2 at the beginning of this, then we return a sequence just containing none, and otherwise then we apply all of the effects and we see if the boss has died. If the boss has died, then we return a sequence just containing some and the amount we've spent so far. Okay, so far not too hard, but then we have to first of all clean up all the spells that we've used. So each spell has a duration it's active for. We reduce that by 1, and then we filter out the spells that have got down to duration of 0. But then if it's my turn, then if it's a part 2, then my health points just go down by 1, and I have to work out what spells I can afford to buy. And I do that by checking, have I got enough to buy it, and is that spell active? And you'll notice I've added a line in here. I'll explain what that means in a minute. But then we go through each of the spells that are buyable, and if there are no buyable spells, then we return a sequence containing none. But if there are, we then return a sequence which contains the results of every possible game where we buy that spell. So we pick out the spell, we apply it if it needs to be applied immediately, and then if we beat the boss we yield some with the amount spent. Otherwise we recursively call ourselves containing the state of the game as it is currently. And there's a little bit down the bottom here which is the boss's part where he gets to inflict damage upon us. And Lincoln's boss started with health points of 70 and had damage of 10, and when we play this with Lincoln's boss, we get Lincoln's answers, and it runs in about 38 seconds on this not particularly fast computer, will give the answers. However, when I plug my boss in, and my boss is much easier to beat, he's only got a health point of 58 and a damage of 9, this ran for a good hour and 30 minutes with the end nowhere in sight. And basically what I think it is just because my boss is so much easier to beat, there are many more ways that he could be beaten, and many inefficient, redundant ways of beating my boss. And so basically this was just going on forever and ever. It was actually the thing I feared in C# and why I wanted to run every battle in its entirety before moving on to the next one. And so what that meant was, with this algorithm, you could just end up running almost forever. And so just to make it terminate, I put in a hard limit of 1,500. After we've spent 1,500, I'm going to break out of this and say that we can't afford to buy the spell. And that does make it terminate. It returns my answers, and it returned them in about 34 seconds when I ran it. And it would be possible, I think, to fix up Lincoln's solution to keep track of the best answer and to abandon any battles where the current amount paid is more than the best answer. But it would require a little bit of refactoring to, I think, probably put aside on a queue somehow the current state of the battles that are incomplete, and to start off by completing a battle and then going back and resuming all of the battles from earlier points, making different choices and only carrying them on as long as the total amount spent is less than the best so far. And so there we have it. I did get my 2 stars today. I didn't create my own solution in F sharp, and my solution in C sharp arguably was a little bit hacky. However, I think there's quite a few instructive lessons to be learned today about the importance of having code that's easy to debug so you can track down silly mistakes, and also that brute force isn't always going to get you to the solution, because sometimes certain problem inputs will just run for far too long. And so although I love this solution from Lincoln, I think it's really brilliant and clever, it does need to be refactored a bit to work effectively with my boss input. Anyway, thanks for watching, and hopefully I'll see you tomorrow.